Hi everyone. So I think everybody heard me. So I'm here to speak about Windows code signing protection. So first presentation. My name is Paul. I work for CERT Sequoia, and I basically work on malware analysis, incident response, and Windows internals. So I'm here. I work here in Luxembourg. So this talk will be mainly focused on authentic code. So I will shortly explain what is it. I think everybody here knows that, so I'm not going to take a lot of time on it. So it's the code signing mechanism developed by Microsoft on basically Windows system. It's based on certificate, and you have, as every certificate, a support expiration date, a system of revocation list. So if certificate provider is compromised, you can revoke all certificates signed by this one, extra. So it's not really what interests me on this topic. I will more focused on the implication on the kernel space and userland space of Windows signatures. Especially for kernel space, I will speak about the driver signature. In fact, since Windows 7 64-bit, you must sign your binary, your driver, to be loaded by the system. If it's not signed, theoretically, you are not able to load it. At the end of the presentation, I will do a short presentation about the user mode implication. Since few Windows release, you have an interesting implication of binary signature on the userland too. So I think you all already saw this kind of screenshot with when you try to execute with administrator privilege, a signed binary, you have the name of the publisher, extra, and you must validate. If the binary is not signed, you have the yellow box at the here. Don't know. Yeah. So the kernel space implication. So as I mentioned, since a lot of years, Windows 7, you are not allowed to load driver if it's not signed. And signed by a legitimate provider, not self-signed, of course. So does it mean it's the end of rootkit, malware that work in kernel space? Obviously not. We have current rootkit, and the interesting thing is to understand how they deal with this new, not really new, but this current protection on the Windows system. I identified on the few years two main ways to bypass this protection. The first thing is a low-cost approach. It's not really efficient, but it works. And you have a really more technical approach that is more interesting for me, and I will explain this one. How works the kernel signatures on Windows? So for obvious reasons, you can disable the signatures. If you are developers, you don't want to sign your driver at each new line of code to be able to load it, test it, crash your system, you patch it, extra. On the process, you cannot sign each time you process your binary. So you can enable something called testing mode by Microsoft with the bcd edit command, as you can see. And when you switch in test mode, so you are able to load unsigned binary, but on the bottom right of your Windows system, you have the text you can see on the screenshot. You have test mode, Windows 7, and the build version. So it's not really discrete. If you switch your system in test mode, you have a huge text that mentions you are in test mode. So if you saw this kind of thing on several of your servers, I think you have a big problem. But anyway, how this text is displayed on your system? In fact, when you log on the system, you have winlogon.exe that is executed, and it's this process that writes this text on your desktop. So one approach that some attackers had is simply to monitor the execution of winlogon.exe and simply patch in memory winlogon.exe in order to never display this message. But you don't have the display, but the signature is really disabled. If you use bcd edit command to check, you can see you are in testing mode. It's not visual, but you are really in testing mode. So for me, it's a low-cost approach because you don't really bypass Authenticode. You simply disable it and hide the message to the users. So another approach, more interesting from my point of view, is used by malware, and it's used by Uroboros or Turla or Snake, whatever the name by AV company. And how does it work? So the malware developers have a malicious driver, and they use a second driver, a second .sys file, a legitimate one, signed by a legitimate company, but this one has a vulnerability. They load this legitimate driver, use the vulnerability in order to switch off the signature mechanism, and after, once it's switched off, they simply load the malicious driver. How does it work really? In this case, the Uroboros developers chose VirtualBox, a vulnerability on VirtualBox, vbox drv.sys, and this vulnerability allows to switch an arbitrary memory address to 0. So why it's interesting for malware developers in this case? It's simply because the code integrity is global flag called G_CI enabled is at 1 when the signature mechanism is enabled and is set to 0 when the signature mechanism is disabled. So what the developer needs to do is to find where is this specific global flag, use the vulnerability on VirtualBox to switch to 0, and the system thinks the signature is disabled and you are able to load the malicious driver just after. So it works. But it's not perfect, because as the developers switch the global flag for the system, the signature is really disabled. So if you use bcd edit to check, bcd edit, I didn't reverse it, but I think this command checks the global flag. So if you execute this command, you will be able to see that the system is really in testing mode, because it's going to check this flag. This flag is set to 0. You are in testing mode. So for incident response team, it's easy to perform a bcd edit on all the machine and check the real value of the global flag on all the system. I suggest to do it. Sometimes you have really funny results. So more in detail how it works. So the VirtualBox driver creates a symbolic link called vbox_drv, and the bad guy will use this symbolic link to overwrite the global flag address. And you simply have the device I/O control, and it's all. You have all the code on this line. You use the symlink, you have the global flag address, and it's going to switch to 0. You have a complete implementation on kernel bound. You can simply copy paste it, and it works. You can disable Windows signature on 64-bit version. Few months after I formed this specific approach, I work on another rootkit that works on Windows 64 called derusb. And in this case, the developer used more or less the same approach, but with a different implementation. From my point of view, a better implementation. So they use a vulnerable legitimate driver, as previously. This time it was a novel driver, nicm.sys, with the old CPU 3 years ago. And in this case, the vulnerability is not simply how to switch a specific address to null. In this case, you are able to execute shellcode on kernel space. So I decided to analyze what exact shellcode is executed on the kernel. So I used WinDBG. I decided to breakpoint on device I/O control and check what kind of data are sent to this device, symbolic link. And you can see some value in bold. And obviously, you recognize the shellcode. But I have assembly to help you. So, what does it do? It simply take a value at a specific address in kernel space, perform a OR 8 on this address, and that's all. The shellcode is really small and only does that. When I saw that, first, it's not really common. It's really specific to do something really specific, but I didn't know what is at this address at the beginning and why is this OR 8. It's really weird. So the first thing to do is to see which driver is at this specific address. And if you have to WinDBG, you can see it's ci.dll. CI is for code integrity. So the exploit on this driver, the shellcode, is trying to modify something in memory on the ci.dll library load in the kernel. The second thing is, why is this OR? Here is a simple screenshot of my value before and my value after the execution of the shellcode. So I have got 6, and after the OR, I've got E. Why? So I simply check the code of ci.dll to understand how it works. And it's documentation from Joru, so it's really easy, it's in C. You can see here an internal variable used by ci.dll called ci_options, and the default value set by ci.dll is 4 or 2, 6. So I've got 6, I can see 6 here. And if you look at the code, blah, 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 you can see if you're in testing mode, ci_options is OR by 8. So I got exactly what I mentioned just before. I got 6 at the beginning, I got OR 8, and at the end I've got E, if I'm in testing mode. The second thing is, if I look on IDAPRO, where is stored these ci_options variables, you can see it's stored on dword blah 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 E30. And if you look on the shellcode, what is the address of the patch variable on the kernel? It's the same thing, it's blah blah, and it's finished by E30. So it's not exactly the same address due to the randomization of memory, but the end is aligned. So what the DRSB developers did, in fact, instead of modify the global flag and be triggered by every legitimate tool such as BCDedit, in this case, they decided to patch an internal variable used inside of ci.dll. With this trick, they disable locally the kernel signatures without touching the global flag. So in this case, if you use BCDedit to check on your system, you will see, no, you are protected. But in fact, internally, inside of ci.dll, in the kernel, it's disabled. So after that, you are able to load unsigned driver without any problem. A question I already had a few weeks ago, someone asked me, yeah, but you've got the patch guard on Windows system. You cannot patch kernel memory. If you patch it, it crashes. Yes, the patch guard, for people that don't know that, is a system on kernel Windows. If you try to patch really sensitive structure or code or this kind of thing, the system decides to suicide, and you have a blue screen. But here, as it's variable, it's designed to be changed. It's normal to be able to change this variable, so it's not protected by patch guard. You can modify it without any problem. The system won't crash. So, for me, it's from the different approach I saw until today, it's the most efficient way because it works. It's discrete, and you cannot really check internal variable of internal DLL loaded in the kernel. You can, but for big environment, it doesn't seem to be so easy. Another case concerning rootkit on modern system is Greyfish. theoretically developed by equation group people. But sadly, I don't have the samples. I only have the Kaspersky report mentioned here, and on this report, it's mentioned that to bypass modern OS security mechanism, blah, 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 Greyfish exploits several legitimate drivers, included one from CloneCD, lbcdio.sys, etc., to achieve kernel-level code execution. For me, it sounds really, really similar than previous case. So I think that the guy of equation group used more or less the same technique. They use a legitimate driver to bypass signature, but I don't know exactly how they implement this the bypass. So I asked to Kaspersky if they are okay to share the sample with me. I think it was in March, something like that. And they say, okay, we accept to share the sample with you. But with one T, it's not so easy. I asked in March, and they say, okay. They didn't give me sample. I do the same in April, in May, in June, in July. And in fact, it's okay, but I'm still waiting. So if someone from Kaspersky is in the room, I would like to have this sample, please. Really. So, another request for the room, maybe someone can help me. I got a rootkit developed by the guy behind APT28, Fancy Beer, Sendit, whatever the name, called IDRV. No paper is available about this rootkit, but maybe one of you already work on that. And it's a 64-bit driver, but I don't have the dropper. I only have the .sys file, and I don't have the executable that maybe load the legitimate driver, etc., etc. So if one of you has the dropper, I would be happy to have it to check how this group bypass protection and is able to load this unsigned .sys file. And this file, this driver is developed for Windows 7, so I'm sure they bypass the protection, but I don't know how. Sadly. So feel free to contact me. So, all these malware developers use more or less the same technique as I mentioned, but sometimes you can do things really, really easier. Before explaining how I would do if I was a malware developer, some question I already has on the several presentation. The thing is, what about expiration date? You saw the CVE. The CVE was really old. The VirtualBox vulnerability was from 2008, I think. So the certificate is expired, and directly it's not a problem anymore. However, the expiration date is not supported by Windows kernel. So even if your driver is expired, you can load it without any problem. And in fact, it's for a production point of view. Imagine you have a factory with a really old system, and if you don't patch it one day, because the certificate is expired, everything is done. So that's why you are able to load expired binary. I don't know if you can set a flag somewhere in the registry, or I don't know if something exists to force expiration support. I didn't find, but maybe you should ask to Microsoft people. Another thing people ask me often is, yeah, but we have a revocation list. Yes, we are. But who really care about revocation list first? And I make some tests, and in fact, it seems to doesn't work. Even if I revoke myself, I'm able to load my signed driver. So I think it's like expiration date, it's not supported by kernel. So maybe for you it seems to be a little bit complicated to patch the kernel at a specific address, extra, to simply be able to load driver. Even patch winlogon.exe, maybe it's not so convenient. I got something really easier to play with kernel. I don't know if you remember about this leak a few months ago. It's a leak about, I don't remember which editor, Dell, Lenovo, I don't remember. Someone remember? No? Everybody sleeping? Okay. So, security guys published a paper about embedded certificate on the image of, I don't remember which big computer manufacturer. And they mentioned that inside of the leak, they found certificate from Atheros. It was a certificate used to sign the Bluetooth legitimate driver of Atheros. And on this leak, everybody spoke about potential man in the middle, because you have certificate and I got a private one, extra. But everybody forget to mention that thanks to this certificate, I'm able to sign every driver and load it. On the article, you can see it's expired since 3 years, but in fact, it's not a real problem. You can load expired binary. You can load binary with expired certificate. It's not supported. The expiration is not supported. So you can simply take the certificate inside of this zip, and they provide the password is t-span. Sign your driver, and you will be able to load it. Even today, it works without any problem. And you don't have to use kernel patch, assembly, or what you wish. You simply need to sign with Visual Studio if you wish, and it works without any problem. So, the future. We are waiting the future since a lot of time. And on every Windows release, Microsoft explained that it's going to change. But even today on Redstone Edition, few released in August, I think, it's not implemented, but the dream of Microsoft is to only load drivers signed by Microsoft. So if you are a driver developer, you create your driver, you test it in testing mode, etc. And at the end, you send it to Microsoft. They validate, I don't know really how, and they will sign the certificate for you, and this one will be able to be loaded on every system. So if you are registered to IT Insider, you will see that this topic come at every release. This topic come back, but today it's not implemented. But maybe one day. So I spoke about kernel space implication, and since Windows 10 threshold, you have another new implication on Windows, on userland space. Since Windows 8, you have something called protected process, and in fact, it's like the name explains. You have processes that are specifically protected against reading in memory the content, etc., etc. To enable that feature, they use certificate. They use authenticate. You have a really good documentation from UNESCO on its website, and I'm not going to speak about the implementation. So now, if you check on digital signature details, certificate, etc., etc., you have a specific value with, I don't know, protected process like verification, I don't really remember which one. And what does it mean? It means that when you perform an open process, you are not able to make a process all access, for example. You are not able to read memory of a remote process. But you are allowed to make something called query limited information. You are allowed to ask several specific information, like his name, his PID, etc. You are able to ask this simple information. But you cannot say, I would like to read all your memory and check what you are doing now. It's only available for Microsoft binary. You cannot create your own tool and say, I would like to be a protected process. No, you must be signed by Microsoft. So it's only for Microsoft. Something new that appear in Threshold 2 version of Windows 10 is a protection inside of Edge, the new Windows browser. And they implemented a protection against binary injection. You have a blog post from Microsoft that explains, and it explains that the latest, it was not the latest today, but the previous one, update of Microsoft Edge have enforcement against loading unauthorized DLL into Microsoft Edge content process. Okay, why not? But I asked me, how does it work? How they implement this feature? And I published an article about how it works, etc., because I didn't find any documentation. And I make a mistake on my paper. I used the word undocumented. And UNESCO read my article and say, why do you use undocumented? It's in WinNT.H. So it's documented. If it's in the SDK, it's documented. So it depends on your point of view. If you think that the .h file from Microsoft is the documentation, it's documented. If you think it's not official documentation, it's not documented. So it's a point of view. So how does it work? Now on process, you have a mitigation policy structure on each process that explain new protection provided by Microsoft. One of these flag is signature policy, something like that. Yeah, process signature policy. And on this element of the structure, you have a flag. And this flag is Microsoft signed only. Yeah, it's clear. Store signed only, Windows Store, it's clear, etc. So now you have specific flag on the Windows system that explain if it's protected by Microsoft signed only, by Store only, or if it's not protected at all. How does it work in really? When you make a load library inside of this kind of protected process, inside of Edge, for example, if you try to create load library, it's asked for memory allocation to store this library inside of the process. And during the creation of the memory allocation, it uses CI.dll, so code integrity. And if the library you try to load in memory is not signed by Microsoft, for example, the memory allocation failed, and you cannot load library. So, is it bulletproof? So, yes and no. It depends, in fact. If you try to load a library inside of Edge with load library, it works. Yeah, the protection works. You cannot load the library. So, for example, from several pub that add advertising on your web page, that create toolbar or whatever, it's good enough because they basically make a DLL injection, they open the browsers, make a load library and ask to the browser, could you load this library and execute it? And it injects stuff inside of your browser. So it protects well against this kind of approach. But if you make what I called on my Slack a dirty injection, so not a real library, but for example, shellcode injection or memory patching, etc., it does not work because you never used load library. So it's a real protection against load library execution, but not against shellcode execution. If you want to perform shellcode execution, it's not a problem. If you want to test, on our GitHub account, I create a binary injection mitigation project, and it's simply an injector with two options. One option is I want to use load library with this library, and the other is I want to use a shellcode, and you put the shellcode in second argument. And you can test if it works, and if the load library is protected, or not. So it's basically the new feature from the TH2 update of Windows 10 and about the protection against binary injection. So yeah, it works, but it's not perfect. So basically, I finished the presentation about these two way of protection about kernel space and how malware developers can bypass it, and the new user space approach and the new user space implementation on Windows signatures. So if you have questions, feel free. Awkward science is good for me too, I'm used to. Or you can applause to wake up your neighbor.
Questions, come on.
I was so clear.
Well, thanks, Paul.